A colossal stone block fits its neighbor so perfectly not even light passes between them. How did ancient builders create this impossible precision without any modern tools? This video uncovers the 10 ingenious principles that guided the master stoneworkers of our past. By the end, you will see these ancient ruins as a testament to a kind of human genius we have nearly forgotten. We will explore how they cut granite with string and sand, and how they moved mountains of rock using only physics and patience. What profound knowledge about stone and geometry has been lost to time? These structures stand as a silent challenge to our understanding of history. Look closely at the zigzagging walls of Sacsayhuaman, high in the Andes. Each stone, some weighing more than 100 tons, is not merely stacked. They are carved with complex, asymmetric faces that lock into their neighbors above, below, and beside them with a snug, organic fit. This is a three-dimensional stone puzzle assembled on a mountainous scale. Then, travel to the heart of the Great Pyramid and examine the granite boxes often called sarcophagi. Their interior surfaces are flawlessly smooth, with corners so precise they meet at perfect 90-degree angles, all worked from a single, incredibly hard block. This is not chance or crude craftsmanship. This is the signature of a deliberate, sophisticated process. We are looking at the work of master engineers. Yet here lies the heart of the mystery. These accomplishments appear in the archaeological record thousands of years before the concept of a standardized inch or centimeter was established, long before the invention of precision steel tools or even the common tape measure. So we are faced with a compelling paradox. The physical evidence is right before our eyes, undeniable in its perfection. But the historical toolkit we typically credit to these cultures seems utterly insufficient to explain it. This gap between what we see and what we thought we knew is where our real exploration begins. To bridge that gap, we must temporarily set aside our modern assumptions about technology and measurement. We must be willing to consider that these builders operated from a different, yet profoundly effective foundation of knowledge. Their precision did not come from a ruler we would recognize. It came from principles embedded in the natural world itself, principles they learned to see, to feel, and to harness. This profound understanding of stone began with a simple, yet revolutionary idea. They saw the rock not as an obstacle to be conquered, but as a partner in the process. Think of a master woodworker selecting a piece of oak. They don't just see a block, they see the direction of the grain, they feel the density, they anticipate how it will respond to the chisel. Ancient stone engineers possessed that same intimate knowledge, but for granite, limestone, and basalt. Their first and most fundamental principle was a mastery of material science, born from countless generations of hands-on experience. They became geologists long before the word existed. For the builders of the pyramids, this meant knowing that the fine, white limestone from the Tura quarries across the Nile was perfect for the smooth, outer casing stones that would gleam in the sun. They understood it could be cut and polished to a brilliant sheen, but for the immense inner chambers, the weight-bearing sarcophagi, they needed something vastly stronger. They turned to the granite quarries of Aswan, hundreds of miles to the south. This stone was a beast, incredibly hard and durable, but they knew its secrets. They learned to identify its natural cleavage planes, the hidden lines of weakness within the rock where it would most willingly split. This wasn't guesswork, it was a deep, tactile science. They knew which stones would fracture cleanly with a well-placed strike, and which could be ground and polished to that impossible, glassy smoothness we find inside the pyramid's granite boxes. They weren't fighting the stone's nature, they were collaborating with it, turning what we might see as flaws, the grain, the cleavage, into the very guides for their precision work. This intimate partnership with the material was the essential foundation. Without this first principle of knowing the stone better than you know your own tools, none of the other engineering marvels would have been possible. This deep, tactile knowledge of stone was only the beginning. To transform raw rock into architectural perfection, they needed a universal language, a system of rules that could be shared, taught, and replicated with flawless accuracy across generations of builders. They found this language not in a numbered ruler, but in the timeless truths of geometry. This was their second principle, the geometry of perfection. Without standardized inches or centimeters, they turned to the pure relationships of shapes, proportions, and angles that exist independently of any man-made tool. Their measuring devices were elegantly simple because the principles themselves were immutable. A length of cord, for instance, was far more than rope. Stretched between two stakes, it defined a perfectly straight line. Tied with a series of evenly spaced knots, it became a giant, flexible compass. By fixing one knot as a center point and pulling the cord taut, a worker could scribe a perfect circle on the ground of any size needed for the project's foundation. That same knotted cord could instantly generate perfect right angles, the absolute cornerstone of stable construction, through a method known as the 3-4-5 triangle. If you take a cord with 12 equally spaced knots and form a triangle with sides measuring 3 knots, 4 knots, and 5 knots, the angle between the 3 and 4 knot sides is always a perfect 90 degrees. This is the Pythagorean theorem in physical form, a practical truth these builders used millennia before Pythagoras gave it a name. With this simple cord, a master could walk onto any chaotic building site and within moments establish a true square corner from which every other wall and alignment could be derived. This geometric thinking scaled from the smallest detail to the grandest vision. By creating these perfect geometric templates on the ground, they established a master reference frame. Every stone cut, every wall raised could be checked against this invisible network of true lines and angles. Consistency was not achieved by measuring each stone individually with a stick, but by ensuring every piece conformed to the overarching geometric plan. The true guide for these ancient engineers was not an arbitrary unit of length, but mathematical truth itself, a constant and reliable partner that turned intuition into precision, one perfect angle at a time. But geometry alone could not carve the stone. A perfect right angle on the ground is one thing. Transferring that perfection onto a rough, multi-ton block of granite is another challenge entirely. This brings us to the third principle, the art of precision drafting and templates. How do you communicate a complex, irregular shape to an entire team of stonecutters, some of whom may be working miles from the construction site? The ancient solution was breathtakingly direct and foolproof. They drew the building full size before a single stone was set. Evidence from sites across the world points to the use of what we might call a mason's drawing room. Imagine a large, flat courtyard or a specially prepared wall covered in a smooth layer of plaster. On this giant canvas, master architects would sketch the exact life-size profile of every single stone needed for a wall, an arch, or a decorative element. This was not a small schematic, it was a one-to-one map of the final product. Every curve, every angle, every interlocking joint was rendered in precise detail at its actual, final dimensions. Think of it as the ultimate shop drawing, a full-scale blueprint laid out on the ground. This process served a profound purpose. It allowed the master builders to solve all the three-dimensional puzzles of fit and alignment in 2 dimensions first, working out any problems in plaster and pigment rather than in irreplaceable stone. Once the drawing was perfected, it became the absolute reference. A craftsman could then take a simple wooden board or a thin piece of slate and trace the unique shape of, say, stone number 47 from the master drawing. That wooden shape became a template, a physical guide that could be carried to the quarry. A stonecutter would hold this template against a rough block and scribe its outline directly onto the rock face. His job was now beautifully simple and perfectly clear. He did not need to understand the grand architectural vision. He only needed to skillfully remove every bit of stone that lay outside the scribed line. The template guaranteed that his uniquely shaped block would fit only one place in the grand design, and that it would fit perfectly. This system decentralized precision. It turned the entire chaotic site into a coordinated factory where dozens of teams could work simultaneously on different stones, all with the absolute confidence that when the blocks finally made their journey to the rising wall, they would click together like pieces from a single, gigantic puzzle. The true genius was in the transfer of knowledge from the master plan on the wall to the portable template in hand, to the immutable truth of the finished stone. The template guaranteed a perfect shape, but that shape was still locked inside a mountain. The fourth principle reveals how ancient builders liberated these forms, not with brute strength, but with brilliant physics. They were masters of mechanical advantage, using simple machines to amplify human effort with incredible control. The lever, the inclined plane, and the roller were their silent partners, turning impossible tasks into exercises of precise, manageable force. Consider the challenge of dressing a stone surface to that flawless, mirror-like finish we see in the finest artifacts. They achieved this not with power tools, but with a profound understanding of abrasion. A long, perfectly straight wooden beam could serve as a giant sanding block. Workers would spread a wet slurry of sand, a material harder than the stone itself, across the surface. Then, with a team moving in unison, they would drag the heavy beam back and forth in long, steady strokes. Each pass acted like countless tiny chisels, grinding the high points down with relentless, even pressure. This method did not require a single master artisan. It relied on the consistent, amplified force of the simple machine, the beam as a lever, to achieve a flatness no hand tool could match. The same clever thinking applied to moving the Titans. To transport a 100-ton block, they did not simply pull harder, they worked smarter to overcome friction. Evidence suggests they might have prepared a trackway, lubricating it with wet clay to create a slick, plastic surface, or they placed the colossal stone on a bed of wooden rollers, effectively turning sliding friction into the far easier rolling friction. A small team, using ropes and leverage, could then coax the block forward with a steady, controlled motion that prevented damaging jolts or shifts. This controlled application of force was critical. A sudden, jarring movement could crack a prized block destined for a precise interlocking joint, but a smooth, machine-aided glide preserved the integrity of those carefully crafted edges. This is the hidden genius, the application of simple physics not for raw power, but for delicate, deliberate control. It allowed them to apply immense force with a gentle touch, ensuring the precision born in the quarry survived the arduous journey to the wall. Yet even with these simple machines, a stubborn question remains. How did they cut and shape granite, a stone so hard it can blunt modern steel tools, using only copper chisels? The answer lies in a fifth principle, a lost art of material science that turns our understanding of ancient technology on its head. They mastered abrasive technology. The secret was not to find a metal harder than the stone, but to use the stone itself, or rather, minerals even harder, as a hidden blade. Imagine trying to cut a piece of glass. You would not use a softer material like wood. You would use a diamond because diamond is harder than glass. Ancient engineers applied this exact principle, but on a monumental scale. They discovered that quartz sand, crushed garnet, or a mineral called emery, which we know as corundum, were all harder than granite. These became their invisible cutting tools. The process was one of controlled grinding, not chopping. A worker might take a flat copper saw, but instead of relying on its soft edge to cut, they would pour a wet slurry of quartz sand and water into a groove on the stone. As they pulled the saw back and forth, the hard quartz particles embedded themselves into the softer copper. Suddenly, that copper blade was transformed into a moving sheet of countless microscopic, diamond-hard teeth, each one grinding away a tiny speck of granite with every stroke. This same method worked for drilling. A hollow reed or copper tube would be rotated or pumped back and forth over a spot, fed with an abrasive slurry. The tube would not cut the stone. The swirling sand at the tip would grind a perfect circular core out of it, leaving behind those distinctive, cylindrical drill holes we find in ancient artifacts. This technique granted them unbelievable control. It was slow, yes, requiring immense patience, but that slowness was its greatest strength. A craftsman could guide the cut with precision, following a scribed line to create a perfectly flat surface for a joint, or painstakingly grind out the delicate curves of a hieroglyphic inscription, achieving those crisp, sharp edges that look almost machined. They were not cutting stone in our modern sense. They were literally wearing it away, particle by particle, using the very minerals of the earth to reshape it. This was not a limitation of their technology. It was the pinnacle of it, a perfect marriage of material knowledge and relentless, human-guided process. But shaping the stone was only half the battle. The final, breathtaking precision of those seamless joints represents a sixth principle, a quiet manipulation of nature's own forces. To achieve a fit so tight that mortar was unnecessary, ancient engineers may have enlisted two of the most fundamental elements, water and temperature, as their final, invisible craftsmen. Think of the challenge. You have two massive granite blocks, each weighing tons, with surfaces that are roughly shaped and nearly touching. How do you close that last, microscopic gap to create a bond that defies a knife blade? One compelling theory points to the simple, awesome power of expansion. In regions with cold nights, after positioning the stones, workers might have poured water into the narrow space between them. As the temperature dropped, that water would freeze, and as you may know, water expands when it turns to ice. Trapped within the stone embrace, this expansion is not gentle. It creates tremendous, even pressure against both faces. This relentless force could act as a nature-powered hydraulic press, slowly, incrementally grinding the high points of each stone against the other until they wore down into a perfect, custom-fit embrace. Come morning, the ice would melt and drain away, leaving behind two blocks locked together with a precision no hand tool could ever achieve. The stones, in essence, finished each other. A related technique for fine-tuning shape involved a controlled use of thermal shock. If a specific area of a stone needed just a little more material removed, a worker could build a small, focused fire against that spot. The intense heat would cause the outer layer of the rock to expand rapidly. Then, by dousing the heated area with cold water, that outer layer would contract just as quickly, creating internal stresses so great that a thin, precise sliver of stone would pop right off. This was not crude smashing with a hammer. It was a delicate operation using differential expansion, like carefully scoring glass before it snaps cleanly. These methods reveal a mindset that saw the environment not as a set of obstacles, but as a toolbox. They understood the hidden potentials within water's phase change and stone's response to heat, harnessing these slow, powerful, and utterly predictable natural processes to perform the final, most delicate adjustments. It was patience married to physics, a willingness to let nature do the meticulous work over hours or days, resulting in joints that have remained immovable for millennia. Yet even the most perfectly shaped block is vulnerable. A single, sharp jolt during its long journey from quarry to temple could shatter months of careful work, ruining a precisely cut joint or cracking a vital cornerstone. This ever-present danger gave rise to a seventh principle, a logistical philosophy of profound wisdom. Precision did not begin at the wall, it began at the source with a strategy of selective quarrying and on-site finishing. Ancient engineers understood that the safest way to move a mountain was to move as little of it as possible. If you visit an ancient quarry today, you can still read their logic in the stone. Look closely at the bedrock. You will see the ghostly outlines of partially carved blocks still embedded in the living rock, like a sculptor's preliminary sketch. This was their masterstroke. Before a block was ever freed, teams would perform the bulk of the rough shaping right where it lay. Using stone mauls and an ingenious technique involving abrasive ropes, likely ropes soaked in wet sand and sawed back and forth, they would cut deep channels or trenches around the desired block, defining its basic dimensions and freeing it on all sides except the bottom. They would leave it attached to the bedrock by a few strategic points of stone, acting as natural keystones or supports. In this state, the block was stable, secure, and already significantly lighter than a raw, cubic mass of stone. Only when everything was ready for transport would these final keystones be broken, allowing the block to be carefully levered onto its sled or rollers. This method minimized a critical risk. A rough, irregular block is far more likely to catch or snag during movement, transmitting damaging shocks through its structure. But a block that had already been dressed to a smoother, more regular shape in the quarry could glide more predictably. The heavy, dangerous work of removing the excess bulk was done in the controlled, stable environment of the quarry floor. Then the partially finished block would begin its journey. Its destination was not the final wall, but a designated dressing area, a kind of workshop in the shadow of the rising construction. Here, in this controlled staging ground, the master craftsman would perform the final, precise shaping. Using the full suite of techniques, abrasive saws, grinding stones, and their geometric templates, they would transform the rough quarry block into a finished architectural element. They would carve the intricate interlocking joints, polish the surfaces that would be visible, and ensure every angle met the master plan's demands. This philosophy of rough it out there, finish it here was a triumph of risk management. It recognized that transport was the most hazardous phase of the entire operation, a gauntlet of unpredictable terrain and immense forces. By postponing the delicate, precision work until the stone had safely completed that perilous journey, they protected their most valuable asset, the integrity of the final fit. The quarry gave them the raw form, but the dressing yard, a calm space of focused skill, gave it perfection. Even the most meticulously prepared stone could hold a hidden flaw. A subtle curve in its surface, invisible to the eye, would only reveal itself when pressed against its neighbor, leaving a frustrating gap or an uneven seam. For the final, legendary precision, ancient builders relied on an eighth principle, a patient and brilliant system of trial fitting and incremental adjustment. They understood that perfection was not a single act of creation, but a process of refinement. The assembly of a wall was not a one-way journey from ground to final position. It was a careful, deliberate dance of placement and correction. Evidence from sites around the world suggests a remarkably methodical approach. Each stone, likely marked with a mason's symbol or a number for identification, would be carefully hoisted into its approximate position in the rising wall. But it would not be set permanently, not yet. Instead, it would be temporarily supported, perhaps on wooden cribbing or small stone shims, allowing it to be lifted away again. In this tentative placement, its true relationship with the stones around it became clear. The builders then used a simple but ingenious diagnostic tool, a colored pigment. They might have smeared a paste of red ochre or another natural dye onto the face of the already set stone. Then they would gently lower the new block against it. When they raised the new block away, the pigment would have transferred onto the high spots, the areas where the two surfaces actually made contact. Those bright spots on the raw stone were a map of imperfection, showing the craftsmen exactly where material needed to be removed. It was a perfect feedback loop written in color. The stone would then be lowered back to the ground or to a nearby work platform. Using flat grinding stones and abrasive sand, masons would carefully wear down only those marked high points following the pigment's guide. This was not guesswork, it was a targeted, surgical removal of material. They might also use a perfectly flat reference surface, a large slab of polished stone known as a truth plane, to check the flatness of their work as they went. Then the process would repeat: lift, test, mark, lower, adjust. This cycle might happen several times for a single, critical stone. It was slow, it was laborious, but it was utterly reliable. With each iteration, the contact area between the two stones grew larger and more uniform, until finally, the pigment would transfer in a perfect, even smear across the entire face. Only then, when the fit was flawless, would the final bedding layer of mortar, if used at all, be applied, and the stone settled into its eternal home. This method transformed the entire construction site into a giant, three-dimensional puzzle where every piece was custom finished to its specific place. The legendary hairline joints were not a lucky accident of superb initial carving. They were the guaranteed result of a patient, iterative process that accepted no gaps, tolerated no errors, and understood that true precision is always a conversation between the ideal plan and the stubborn reality of the material. Precision was not just an idea, it was a physical reality they could hold in their hands. This leads us to the ninth principle, the creation of specialized tools and jigs. While we often picture simple hammers and chisels, the true mark of an advanced engineering tradition is the development of instruments designed for one specific, critical task. These were the devices that turned human skill into repeatable, flawless action. Take the simple plumb bob, a weight suspended from a string. Gravity pulls it toward the Earth's center, creating a perfect, unwavering vertical line. This tool was indispensable. When building a wall 10 stories high, a builder could hold a plumb line against its face at any point and instantly see if it was leaning even a fraction of an inch out of true. For larger projects, they might have used an A-frame, a wooden structure with a plumb line hanging from its apex. When the legs were set on level ground, the centered plumb line confirmed the frame itself was perfectly upright, creating a giant, portable reference for verticality that could be sighted across an entire site. But a building needs perfect horizontals as well as perfect verticals. For this, they employed one of the most elegant tools ever devised, the water level. It uses a fundamental truth of nature that water always seeks its own level. Imagine a long, flexible tube, perhaps made from animal gut, filled with water and held at both ends. Even if the two ends are 100 feet apart, the water surface inside each open end will settle at exactly the same height relative to the earth. By marking that height on a post at one location, a worker could walk to any other point, adjust the tube until the water at his end matched the mark, and know he had established a perfectly level reference. This allowed them to create a true horizontal plane over undulating ground, ensuring that the foundation for a massive wall or the floor of a grand hall was flawlessly flat from one end to the other. Then there were the master references themselves, the straight edges. These were not ordinary pieces of wood. They were carefully selected, seasoned, and painstakingly crafted to have at least one edge that was as straight as humanly possible. How do you make a straight edge without one to begin with? The answer lies in a process of incremental refinement. A craftsman might start with 3 roughly straight boards. By rubbing the edge of one against another with abrasive sand between them, high spots would wear down first. By repeatedly comparing and adjusting all 3 against each other, they could arrive at 3 edges that were all perfectly straight and true. These became the gold standard, the physical embodiment of straightness against which every other surface on the project could be checked. But perhaps the most clever innovation was the jig. A jig is a guide or a template that controls the path of a tool. Its purpose is to remove human inconsistency. Think of a modern key-cutting machine. It holds the blank key and the guide key in a fixed relationship so the copy is perfect. Ancient builders used this same concept. For drilling a series of identical holes at a set depth, a wooden guide could hold the drill shaft perfectly vertical and stop it at the precise moment. For carving the intricate, repetitive symbols of a hieroglyphic inscription, a craftsman might use a small, reusable template. He would trace the outline onto the stone, and then a carved guide could even help control the depth and angle of his chisel for each stroke. This ensured that every symbol in a long text was uniform in size, style, and depth, a consistency that screams of systematic engineering, not freehand artistry. These specialized tools and jigs were the final link in the chain. They translated the grand geometric plan and the patient process of fitting into daily, actionable steps. They guaranteed that the precision conceived by the master architect could be faithfully executed by every single worker on the site, turning a monumental vision into a tangible, enduring, and impossibly precise reality. All these tools and techniques, however brilliant, were ultimately inert without the most vital component of all, the human hand and mind that guided them. This brings us to the final, and perhaps most profound, principle, the human factor of skill transmission and guild knowledge. The precision we marvel at was not an accident of a single genius, but the direct result of a living system, a river of wisdom that flowed from one generation to the next. This knowledge was not written in books for anyone to find. It was guarded, cultivated, and passed down through a sacred chain of apprenticeship, often within closed guilds or tightly knit family lineages. Think of it not as a set of instructions, but as a culture of craftsmanship. A young boy entering a mason's workshop did not simply learn how to swing a hammer. Under the watchful eye of a master, he embarked on a years-long journey of sensory education. He was taught how to truly see the stone, to read its color and grain like a map. He learned to feel its resistance through the handle of his tool, understanding the subtle vibration that signaled a clean strike versus one that would cause a hidden crack. He memorized the sounds, the distinct ring of a chisel biting correctly into limestone versus the dull thud that meant his angle was wrong. This was embodied knowledge, a fusion of tactile feedback, refined visual judgment, and deep, unwritten tradition. Through endless repetition and correction, the apprentice's own body became calibrated. His eye could estimate a width to within a fraction of an inch. His hand, guiding a grinding stone, could sense the departure from flatness long before it was visible. These artisans became living, breathing, measuring instruments. Their judgment, honed over a lifetime, achieved a level of intuitive precision that we today outsource entirely to digital calipers and laser levels. This system ensured consistency across centuries. The master was not just passing on a technique, he was passing on a standard, a philosophy of what right truly looked and felt like. When a master placed his mark on a finished stone, it was a seal of approval that meant this block met the invisible yet unwavering quality benchmark of the entire guild. This closed loop of learning created a stability of technique that allowed grand projects, sometimes spanning the reigns of multiple pharaohs or kings, to maintain a single, unified vision of perfection. The true secret behind the ancient world's precision, then, was not a lost machine or a forgotten blue crystal. It was a living tradition of mentorship where the accumulated genius of countless unnamed masters was poured, drop by careful drop, into the mind and muscle memory of the next generation, creating artisans for whom the line between tool, material, and self had all but disappeared. Beneath the sands of Saqqara, a different kind of precision lies in wait, one that pushes our understanding of ancient capability to its absolute limit. Here, deep inside labyrinthine tunnels carved from the bedrock itself, rest dozens of colossal boxes, crafted from solid granite and basalt, each one a titan weighing 70 tons or more. They seem utterly out of place in their shadowy crypt. It is not their size that stuns modern engineers, but their finish. Run your hand along the interior surface of one of these boxes, and you would feel a flatness so absolute it defies belief, a smoothness that rivals modern machine polishing. The corners where the walls meet are not merely close, they are geometrically perfect 90-degree angles, sharp and true. And then there are the drill holes, bored into the sides with such consistency that they bear the unmistakable, fine spiral grooves of a tool that rotated under immense, controlled force. These are not the rough artifacts of a primitive culture. They are the products of a manufacturing process of startling sophistication, a case study that demands we look again at the principles we have just explored, especially the mastery of abrasive technology. The sheer symmetry of these boxes whispers of a guiding system beyond hand-eye coordination. To achieve such flawless internal geometry, the craftsman likely employed a form of large-scale compass or a pivoting cutting arm. Imagine a sturdy wooden beam anchored at a central point on the workshop floor, acting as a giant radius. A cutting head loaded with an abrasive slurry could be fixed to the end of this beam. As the beam swept through an arc, the cutting head would grind a perfect, consistent curve into the stone. This same principle, applied linearly with a guided beam, could produce those impossibly straight edges. The tool was simple, a beam on a pivot, but the concept was pure precision engineering, using geometry to govern the abrasive process. Yet it is the drill holes that truly shatter conventional timelines. These are not the rough, conical depressions made by a handheld drill being wobbled back and forth. They are deep, cylindrical bores with parallel sides and those telltale, even spiral striations running their length. This pattern is a fossilized signature. It tells us the drill did not just turn, it was fed downward into the incredibly hard granite under significant, steady pressure, while simultaneously being supplied with a constant stream of abrasive slurry, likely quartz sand in water. The spiral grooves are the path of individual abrasive particles, caught and dragged by the rotating tool, grinding their way relentlessly downward. This implies a mechanism capable of both sustained rotation and controlled, weighted advancement, a technology far beyond a worker simply twisting a bow drill by hand. It suggests a setup with weighted levers or even a simple lathe-like apparatus, where the drill bit remained perfectly aligned as it ate into the stone over what must have been days of continuous, patient operation. The boxes of Saqqara stand as silent, physical rebuttals to any notion of crude antiquity. They are the culmination of the principles we have walked through, a perfect storm of material knowledge, geometric control, and advanced abrasive technique. They show us that ancient engineers did not just approximate perfection, they could achieve it on a monumental scale in the hardest stones on Earth, and they could do it repeatedly, creating not one but dozens of these flawless containers. What purpose they served remains a topic of quiet discussion among researchers, a mystery wrapped inside an enigma. But their existence is no mystery, it is a fact, a cold, hard testament carved in granite that challenges us to rewrite the story of human innovation, not with speculation, but with the undeniable evidence left behind in stone. The granite boxes of Saqqara are a marvel of controlled, geometric precision, but halfway across the world, a different kind of stone mastery whispers from the mountains. High in the Peruvian Andes, the walls of ancient sites like Sacsayhuaman, Ollantaytambo, and Cusco present a puzzle that seems to reject all our usual rules of construction. Here, builders worked with a chaotic array of stones, each one a unique, irregular polygon with anywhere from 6 to 12 sides, some weighing over 100 tons. Yet when placed together, they interlock with such snug, organic perfection that you cannot slip a piece of paper between them. This is polygonal masonry, and it represents a philosophical departure from the right angles of Egypt. Instead of forcing nature into a rigid geometric grid, the Andean engineers embraced its beautiful, asymmetrical complexity, creating walls that move and flow like solidified liquid. The result is not just visually stunning, it is seismically brilliant. During the frequent earthquakes that shake the region, these interlocking walls dance as a single, flexible unit, the stones shifting and settling without collapsing, while more rigid, rectangular constructions would shatter. But this raises an almost impossible question. How do you achieve such a perfect, custom fit between two stones that have no straight lines, no common angles, and no repeating pattern? The answer lies in taking the principle of trial fitting to its absolute, most patient extreme. Unlike a system based on standardized blocks, here every single stone was a one-of-a-kind masterpiece, shaped for one specific location and for the unique contours of the stones already in place around it. The process likely began with the careful selection of a massive boulder. Using stone hammers, workers would rough out a general shape, perhaps creating one relatively flat face that would become the outward, visible surface. But the back of the stone, the side that would marry with the wall, was a different story. This hidden face had to become a perfect, negative imprint of the jagged, irregular puzzle piece already set in the course below or beside it. So how did a mason transfer that incredibly complex, three-dimensional profile onto the new block? One compelling theory involves the use of a soft, impressionable medium, like wet clay or plaster. Imagine a craftsman pressing a large sheet of this material against the already placed stone, capturing every dip, bulge, and angle in a perfect mold. This mold could then be carried to the new block, held against its rough surface, and used as a guide. The stonecutter's task was now clear, yet monumental. Remove every bit of rock that stood outside the boundary defined by that clay impression. An even more direct method might have involved a process called scribing. A mason could have taken a sturdy, yet slightly flexible rod or a length of wood and carefully traced the exact contour of the set stone's edge. Holding this scribed profile steady, he would then transfer that line directly onto the face of the new block, scratching it into the stone. This line became the sacred boundary. His chisel and hammer then worked with meticulous care, not to create a shape from a plan, but to reveal the shape hidden within the stone, the shape that would complete its neighbor. This was a dialogue between two rocks mediated by human skill. They would lift the new block, test its fit, and see where it still made contact. They would lower it, grind down those high spots revealed by pigment or by the shiny marks of contact, and lift it again. This cycle of test, mark, and adjust might have been repeated dozens of times for a single, giant stone. The final act was one of immense control, using gravel, sand, and water as a final abrasive slurry, perhaps with teams rocking the massive block back and forth in its socket, letting the stones themselves wear each other into a flawless, seamless union. This was not construction in the sense we know it. It was a form of three-dimensional sculpting on a colossal scale, where the wall itself grew organically, each new stone learning its form from the one that came before. It speaks of a culture that saw harmony not in uniformity, but in the perfect, resilient fit of unique elements, a lesson in strength carved into the very bones of the mountains. The flowing, resilient walls of the Andes speak a language of organic adaptation, but another ancient empire pursued precision with a different kind of genius, one of systematization and scale. From the misty highlands of Peru, we journey to the sun-baked heart of the Roman world, where engineering was not just an art, but a repeatable science applied across a vast empire. While the Romans are rightly celebrated for their revolutionary concrete, their mastery over cut stone reveals a parallel path to perfection, driven by the relentless demands of infrastructure. Here, precision was not a philosophical ideal, it was a practical necessity. A water channel that leaked or an arch that settled unevenly could mean the failure of an entire aqueduct or the collapse of a vital bridge. This pressure forged an approach that blended brute force capability with meticulous control, a system where innovation in tools met an unwavering commitment to standardization. The Roman advantage began with a material leap, the widespread use of iron. Unlike the copper tools of earlier civilizations, iron chisels and saws were harder, more durable, and could hold a sharper edge far longer. This did not mean they abandoned the wisdom of abrasives, far from it. They combined the two, using iron saws with teeth set to act as carriers for quartz sand or emery slurry. This hybrid technique gave them the best of both worlds, the aggressive cutting power of metal enhanced by the relentless grinding of hard minerals. It allowed for faster, more repeatable cuts through stone like marble and travertine. Speed, however, was never the enemy of accuracy. To ensure that speed produced consistency, the Romans embraced standardization with an almost military fervor. They developed modular designs. Instead of each stone being a unique sculpture, common architectural elements like column drums, paving slabs, or blocks for a regular wall were designed to interchangeable dimensions. A mason in a quarry hundreds of miles from Rome could produce a standard-sized ashlar block with confidence, knowing it would fit seamlessly with blocks cut by a different team at the building site. This was precision through pre-agreement, a shared language of measurement and proportion that allowed a decentralized empire to build with a unified, efficient voice. This focus on repeatable components demanded equally repeatable processes for moving and placing them. Enter one of the Romans' most iconic innovations, the treadwheel crane. Picture a giant wooden wheel, like a hamster wheel for humans, mounted within a sturdy wooden frame. A team of workers would walk inside the wheel, their weight and motion rotating it. This rotation turned a central axle, which wound a heavy rope attached to a lifting hook. The genius of this machine was its combination of immense power and delicate control. The treadwheel provided tremendous mechanical advantage, allowing a small team to hoist multi-ton stone blocks or heavy architectural elements high into the air. But because the power was generated by human steps, it was inherently controllable. The crew could inch the load upward with minute precision, pause on command, or lower it with gentle care. This controlled placement was absolutely critical. A standard-sized marble block lowered clumsily onto its neighbor could still chip a critical edge, ruining the tight joint. The treadwheel crane transformed the chaotic, dangerous act of lifting into a smooth, orchestrated operation. It ensured that the precision achieved at the quarry bench survived the final, dizzying journey to the top of a rising arch or colonnade. Ultimately, Roman precision served a grand, utilitarian vision. It is etched into the gentle, unwavering slope of an aqueduct channel, carved from stone so accurately that water would flow for miles without pooling or rushing. It is locked into the precise voussoirs, the wedge-shaped stones of an arch, each one cut to exacting angles so that when the final keystone was set, the entire structure became self-supporting, distributing immense weight down through its curves with perfect equilibrium. Their precision was the silent guardian of function. It ensured that public fountains flowed reliably, that harbors remained protected by massive, interlocking breakwaters, and that grand basilicas stood open and airy under the thrust of perfectly balanced vaults. In the Roman world, we see a different facet of the ancient engineer's mind. Here, the quest for perfection was married to the pragmatics of empire, proving that systematic tools, shared standards, and ingenious machines could create a legacy of precision just as enduring as the most mystical stone puzzles, a testament to the power of organized human ingenuity applied on a continental scale. The stone itself was only part of the master plan. For the greatest builders, precision extended far beyond the fit of a joint, reaching upward into the very heavens. This introduces a breathtaking additional layer, precision in orientation. Many of the world's most meticulously crafted structures are also aligned to celestial bodies with an accuracy that seems to defy their ancient age. The Great Pyramid of Giza offers the most famous example. Its four faces aligned almost perfectly to the four cardinal directions, with its north-south axis pointing to true north with an error of just a fraction of a single degree. To understand how significant this is, consider the scale. We are talking about a structure whose base spans over 13 acres, a colossal footprint, yet its orientation is off by less than the width of your thumb if you held it at arm's length. This is not a lucky guess. It is the result of deliberate, patient, and profoundly sophisticated astronomical observation. So how did they establish a true north-south line, a meridian without a magnetic compass, which points to magnetic north, a constantly shifting point that wanders over time? Their compass was the night sky itself. The method likely involved long-term tracking of a circumpolar star, a star that, from their latitude, never sets below the horizon. Instead, it appears to rotate in a circle around the celestial North Pole. Imagine an ancient astronomer, perhaps a priest engineer, setting up a simple but fixed observation point, a leveled platform with a central gnomon, a vertical rod. Night after night, over the course of a full year, they would mark the precise point on the horizon where a specific star, like Thuban in the constellation Draco, which was the pole star at that time, would rise and set. They would not use just one star, but likely a pair of stars. They would wait for the moment when two stars aligned vertically, one directly above the other, passing an imaginary line in the sky known as the meridian. By marking the shadow cast by their gnomon at the exact instant this celestial alignment occurred, and then doing the same on a different night with a different pair of stars, they could bisect the angle between the two shadow lines. That bisecting line was true north-south, a reference drawn not from the unreliable Earth, but from the fixed, predictable clockwork of the cosmos. This celestial calibration was the ultimate act of setting the baseline. Once this true meridian was established and physically marked on the ground with permanent stone sighting pillars or a long, cleared causeway, it became the sacred reference for everything that followed. Every terrestrial measurement, every foundation trench, every wall alignment could now be checked against this cosmic standard. It meant that the pyramid's corner was not just square to the next block, but square to the universe. This astronomical precision was embedded into the very bones of the structure from its first moment. The builders were not just constructing a tomb, they were anchoring their work to the eternal cycles of the sky, creating a monument that was geographically precise on a planetary scale. This fusion of celestial science with terrestrial craftsmanship reveals a holistic vision, where mastery over stone was just one expression of a deeper desire to harmonize human creation with the fundamental order of the cosmos. Aligning a pyramid to the stars was a feat of celestial observation, but feeding the army of hands that built it was a miracle of earthly organization. The breathtaking precision locked in stone was merely the final, visible product of a vast and invisible machine, a machine made of people. To achieve such consistency across decades of construction required a society operating with a different kind of exactness, a social and logistical precision on a national scale. Think of the Great Pyramid not as a solitary monument, but as the apex of a sprawling, living pyramid of human effort. Beneath it stood layers of meticulously coordinated roles. There were the quarrymen who read the stone, the draftsmen who translated geometry into full-scale plans, the master masons who directed the final fitting, and the armies of laborers who moved mountains of material. Each was a specialist, a cog in a grand mechanism, but a cog alone is useless. This machine needed fuel, housing, and flawless coordination. The true engineering marvel, therefore, began not at the construction site, but in the granaries, the bakeries, and the administrative offices. A project lasting 20 years might require a workforce of 20,000 individuals at its peak. Simply feeding this multitude was a logistical puzzle of staggering proportions. Historians note that the organization required to supply bread, beer, fish, and vegetables for such a community, day after day, year after year, would rival the planning for a modern city. This was precision applied to the human condition. ensuring that the energy needed to drag a 100-ton block was present in the muscles of the workers, sustained by a relentless, reliable supply chain. This scale of operation demanded a central authority with the power to marshal resources from across the kingdom. It required scribes to keep meticulous records of tools, materials, and rations. It needed managers and overseers who could translate the architect's vision into daily tasks for thousands. The synchronization was everything. A delay in the limestone shipment from Tura could idle hundreds of workers at Giza. A failure in the tool-making workshops could bring precise carving to a halt. The smooth flow of people, food, and stone along the Nile and its canals was the lifeblood of the project. This logistical framework created the stable, supported environment in which technical skill could flourish. The master mason could focus on achieving a hairline joint only because he did not have to worry about where his next meal was coming from, or whether the next block would arrive from the quarry on schedule. The social engine removed the chaos of survival, allowing the quiet, patient work of perfection to proceed. In this light, the precision of the stones is a testament to more than just craftsmanship. It is the physical echo of a society's ability to organize itself, to plan with a long-term vision, and to harmonize the efforts of countless individuals toward a single, enduring goal. The monument we see is just the skeleton, the lasting fossil of a vibrant, temporary city of purpose that once buzzed at its feet. Yet the sheer scale of this human achievement can feel so immense, so alien to our modern experience, that a tempting shortcut emerges in the popular imagination. When we stand dwarfed by these stone giants, a whisper often follows, suggesting they must be the work of otherworldly hands. This idea, while capturing our sense of wonder, ultimately does a profound disservice to the very people whose legacy we admire. To attribute these wonders to visitors from the stars is to quietly strip our ancestors of their ingenuity, their patience, and their hard-won mastery over the world around them. It replaces a human story of incredible perseverance with a fantasy that requires no explanation at all. The truth, however, is far more compelling. Every single principle we have walked through, from reading the stone's grain to harnessing freezing water, is not speculative theory. Each has been tested and proven in the field by archaeologists and in the workshop by modern stonemasons, using only the tools and materials available in antiquity. A team using a copper saw with quartz sand can indeed cut granite. A group of volunteers with ropes, rollers, and a prepared trackway can move a multi-ton block. The iterative process of trial fitting with pigment produces those legendary seamless joints. These are not mysteries of lost superscience. They are demonstrations of applied physics and relentless human effort. What has been lost to time is not the capability, but the vast body of cultural knowledge, the specific guild traditions, and the social frameworks that made such sustained efforts possible. We have forgotten the feel of the tools, the rhythms of the work songs, the lifetime of mentorship that calibrated a mason's eye. The fundamental principles, however, remain firmly within the realm of human possibility. This inclination toward extraterrestrial explanations often stems from a subtle, modern bias, a form of chronological snobbery. We look back and unconsciously measure the past against the yardstick of our own technology, our fast-paced digital world where precision is instant and effort is minimized. When we see a result that would require immense patience and skill from us today, we struggle to believe it could be achieved without our tools. We underestimate the monumental power of cumulative knowledge passed down over generations, the deep observational skills honed by a lifetime of working with natural materials, and the sheer force of communal purpose that can move mountains literally over the span of decades. To overcome this bias is to open a door to a deeper, richer appreciation. It allows us to see these sites not as abandoned alien landing pads, but as the ultimate monuments to human collaboration, intelligence, and tenacity. They stand as a challenge and an inspiration, reminding us of what we are capable of when we observe the world closely, work together with a shared vision, and are willing to invest not just years but generations in a dream made of stone. The most compelling proof does not come from theories, but from the sound of a copper saw biting into granite today. To move beyond speculation, a group of dedicated researchers have taken a radical approach. They have stepped into the shoes of the ancient builders themselves. Experimental archaeologists like Roger Hopkins, a master stonemason, and Mark Lehner, an Egyptologist, have led hands-on projects that strip away centuries of assumption. Their mission is simple yet profound: to rebuild the past, not in a computer model, but in the dust and sweat of a real-world quarry. They use only tools reconstructed from archaeological evidence: copper chisels that dull quickly, dolerite pounding stones, ropes of natural fiber, wooden sledges, and vast quantities of sand and water. There are no modern shortcuts, no steel reinforcements, no hydraulic cranes. The goal is not to improve upon the ancient methods, but to understand them through the strain in your muscles and the blisters on your hands. In one famous experiment, a team set out to quarry a limestone block similar to those used in the pyramids. Using only dolerite balls, heavy stones about the size of a fist, they pounded a groove into the bedrock. It was monotonous, exhausting work, a relentless rhythm of lift and drop. Yet, hour by hour, the groove deepened. They then hammered wooden wedges into the channel and soaked them with water. As the wood expanded, it created enough pressure to cleanly split the block from the earth. The technique worked exactly as theorized, proving that the quarry marks we see at ancient sites were not symbolic. They were functional instructions. In another test, they tackled the mystery of moving a colossal statue. They placed a replica on a massive wooden sledge and positioned it atop a trackway of lubricated timbers. With a coordinated team pulling on ropes, the immense weight began to glide forward with a surprising ease. The experiment revealed a critical insight. The greatest challenge was not the initial pull, but overcoming inertia, getting the sledge to start moving. Once in motion, the sustained effort was manageable, a fact that would have allowed ancient crews to move in shifts, maintaining a slow but steady progress across the desert. Perhaps the most visually convincing demonstrations involve shaping hard stone. Roger Hopkins, with his lifetime of masonry skill, has shown television audiences how a simple copper saw, when used with a slurry of quartz, sand, and water, can indeed cut through granite. On camera, you can see the abrasive paste turn a dark gray as it loads with stone dust, the proof that it is grinding, not cutting. It is painfully slow, a matter of inches per hour, but the cut it produces is straight and clean. These experiments do more than validate techniques. They recalibrate our sense of time and scale. They make the abstract tangible. You watch a modern team, with all our contemporary impatience, gradually achieve a result that looks impossibly precise, and you understand, the ancient builders were not limited by their tools. They were empowered by their profound knowledge of how to use them. The gap between a copper chisel and a granite block closes when you realize the chisel was never meant to fight the granite directly. It was a delivery system for the real cutting agent, the harder mineral in the sand. These projects provide the missing link in the chain of evidence, a replicable, physical bridge between the blueprint of history and the monumental reality left behind in stone. They transform awe into understanding, showing us that the fingerprints on these ancient wonders are unmistakably human. That modern experiment with the copper saw reveals a deeper truth beyond technique. It forces us to confront a psychological dimension almost alien to our modern mindset, where the most difficult ancient tool to comprehend is not made of copper or stone, but of time itself and immense cultural patience. We live in an age of instant results, where a delayed download feels like an inconvenience. Now, try to internalize a different scale. A single, perfectly fitted granite block in a temple wall might represent an entire year of labor for a dedicated team. The shaping, the grinding, the endless cycle of test fitting, all under the sun, season after season for one stone. This was not an exception, it was the standard. The master plan for a pyramid or a ceremonial complex was not a 5-year business plan, it was a generational covenant. A pharaoh would lay the foundation knowing he might not live to see the capstone placed. His son, and perhaps his grandson, would carry the vision forward. This long-term perspective fundamentally changed the very nature of the work. There was no quarterly report, no rush to meet an arbitrary deadline for a grand opening. This cultural framework granted permission for a profound depth of focus. A mason could, without pressure or reproach, spend weeks or even months perfecting the fit of a single critical joint. He was not being inefficient, he was fulfilling the highest standard of his craft, a standard measured in centuries, not hours. This acceptance of slow, meticulous work created a space for a level of care and attention to detail that is economically unthinkable in our world. It allowed for those 100 tiny adjustments, that final polishing with a finer and finer abrasive paste, the quiet observation of how two stones settled together over a lunar cycle. In this environment, precision ceased to be merely a technical skill. It became a state of mind, a meditative practice embedded in the rhythm of the days and the turning of the years. The value was placed not on speed, but on permanence, on creating something that would speak with silent authority to people thousands of years in the future. This patience was the invisible mortar holding the entire endeavor together, the cultural agreement that some things are worth doing slowly and worth doing perfectly because their purpose is to outlast us all. That immense cultural patience echoes in the quiet workshops of today, far from the roar of jackhammers and power saws. The legacy of ancient precision has never truly vanished. It simply retreated into the care of a dedicated few, the master masons and conservators who keep the old knowledge alive. In the shadows of crumbling cathedrals and along the scaffolds of ancient monuments, a direct, living link to those engineers of the past continues its patient work. This is not about replication for grandeur, but preservation out of profound respect. Modern restoration projects on historic sites across Europe and beyond have become the unexpected guardians of these ancient principles. When a centuries-old gargoyle needs replacing or a wall weakened by time must be stabilized, the solution often lies not in modern concrete, but in a return to the original fabric and the methods that created it. Master masons, often trained through guild systems that trace their lineage back to medieval times, approach the stone with the same intimate understanding. They read the grain of a new piece of limestone, selecting it to match the weathering patterns and strength of the surrounding medieval blocks. They create precise cardboard or wooden templates, tracing the exact, often wildly irregular, shape of a damaged stone so its replacement will be a perfect fit, both structurally and aesthetically. For the final, delicate fitting, they will frequently set aside power tools, reaching for hand chisels, mallets, and rubbing stones to achieve a join that honors the original craftsmanship. This work is a dialogue with the past, a conversation in stone. The ancient knowledge informs every decision, teaching modern conservators how to repair these venerable structures without betraying their spirit. It is a philosophy that prioritizes compatibility and reversibility, using traditional lime mortars that breathe and flex like the old walls, rather than rigid modern cement that can trap moisture and cause further damage. In this careful, reverent practice, we see the 10 principles in action once more, not to build anew, but to sustain what was built with such genius. This living tradition is a testament to the enduring power of that hands-on wisdom, proving that the true measure of ancient engineering is not just in the monuments that survive, but in the timeless craft that still knows how to save them. That living tradition of the master mason's touch now stands at a quiet crossroads. Our world has achieved a level of technical precision the ancients could scarcely dream of, governed by digital readouts, computer-guided machines, and lasers that measure to within a thousandth of an inch. We can manufacture components with a consistency that is flawless, repeatable, and utterly perfect. Yet this perfection comes with an unspoken cost, a form of knowledge lost in the exchange. Our modern precision is, in a profound sense, disembodied. It happens inside a machine, verified on a screen, and confirmed by a sensor. The craftsman no longer needs to feel the stone's resistance through the chisel, or judge a flatness by the way light glides across its surface. That deep, intuitive connection between the maker's hand, the tool, and the material is becoming a fading art. Ancient precision was holistic, a full engagement of the mind, the body, and the senses. A builder did not just know a corner was square because a laser dot said so. He knew it in his bones, from the alignment of shadows at the equinox, from the feel of a perfectly balanced plumb line, from the satisfying ring of a true strike. This was knowledge worn into the muscles and calibrated in the eye over a lifetime. In our reliance on digital verification, we risk atrophying a different kind of intelligence, the ability to judge quality and truth by direct perception. We outsource our certainty to a device. What happens when the battery dies, when the signal is lost, or when the machine's programming lacks the context for an unexpected flaw? The ancient approach offers a lesson in resilient knowledge. A master's trained eye and hand require no external power source, no software update, no supply chain for replacement parts. Their tools were simple, but their understanding was profound and self-contained. This represents a form of sustainability we rarely consider, not just of materials but of skill itself. It is a knowledge system built on observation, patience, and sensory feedback, one that can be passed down and preserved even when the infrastructure of a high-tech society falters. The silent stones of the past remind us that true precision is not just a number on a display. It is a conversation with the physical world, a dialogue we must be careful not to let go silent. Could we, with all our 21st century might, build a new Great Pyramid? The question is a captivating lens through which to view everything we have explored. On a purely physical level, the answer seems an obvious yes. We possess tower cranes that can lift hundreds of tons, diamond wire saws that slice through granite like butter, and laser theodolites that can align a foundation to a precision of a single millimeter. We could quarry the stone, move it, and stack it with a speed that would leave the ancient architects breathless. The brute force engineering is well within our grasp. Yet this is where the thought experiment becomes truly revealing. Matching the physical scale is one thing, replicating the holistic achievement is something else entirely. Our modern approach would succeed, but it would do so by bypassing the very essence of the original feat. We would replace generations of patient, embodied skill with a flurry of computerized machinery and disposable labor. The precision would be achieved not through the calibrated eye of a master mason, but through digital feedback loops and robotic arms. We could create a perfect replica, but the process, the human experience behind it, would be utterly alien. The staggering cost of such an undertaking today underscores this disconnect. It would not be a national project of cultural identity, but a fantastically expensive vanity build, measured in billions of dollars and subject to the short-term cycles of budgets and board meetings. We lack the cultural framework that saw such a monument as a multi-generational covenant, an endeavor where a lifetime of labor was a sacred contribution to a legacy far greater than oneself. We have traded that deep, patient commitment for efficiency, and in doing so, we have lost the social engine that made such sustained perfection possible. The ancient pyramid was not the product of a construction company with a deadline. It was the manifestation of a civilization's worldview, a testament to what humans can achieve when they are united by a purpose that transcends a single lifespan. This is the real challenge their work lays before us. It asks whether our own culture, for all its miraculous technology, still possesses the capacity for that kind of long-term, collective vision, where perfection is not a line item on a spreadsheet, but the only acceptable outcome, no matter how many years or how many hands it requires. The true answer to this ancient puzzle has never been found in a single book or a lone discovery. It emerges instead from a modern meeting of minds, a collaboration that finally breaks down the walls between separate worlds of knowledge. For too long, the mystery of ancient precision was trapped in academic silos, with each field holding a piece of the map but unable to see the whole territory. Archaeologists could meticulously document the tool marks left on a stone, but they might not fully grasp the physics behind the force that made them. Engineers could calculate the exact tolerances and stresses, but they could miss the practical, on-the-ground reality of working with a copper chisel that dulls after a few strikes. The missing link, the vital key, has proven to be the voice of the craftsperson, the practicing stonemason whose hands remember what theory can only describe. This fusion of disciplines has sparked a quiet revolution in our understanding over the last few decades. It is a renaissance built not on a single brilliant insight, but on the patient conversation between the scientist's scanner and the artisan's calloused hands. Imagine an archaeological team at a site like Giza. They uncover a limestone block with a series of curious parallel grooves. The archaeologist documents their spacing and depth. The engineer then models the force required to create such a mark with a stone tool. But it is the master mason invited to the site who picks up a replica dolerite pounder, feels its weight, and demonstrates the specific rocking, grinding motion that perfectly reproduces that exact groove pattern. The mason explains that this isn't a random hammering. It's a controlled technique to gradually dress down a surface, a nuance invisible in the static mark but screamingly obvious to someone who has spent a lifetime shaping stone. This is where the magic happens. The engineer's calculations validate the feasibility, the archaeologist's context dates the method, and the mason's tactile wisdom brings the silent stone back to life, revealing the intention in every strike. Or consider the enigma of the stone boxes at Saqqara. Laser scans can map their flawless flatness to microscopic levels, producing breathtaking digital models. An engineer can analyze those models to confirm the geometric perfection, but to understand how that flatness was achieved, researchers turn to craftsmen who still work granite with traditional methods. These artisans demonstrated how a team using a long, straight wooden beam and an abrasive slurry could, through sustained, coordinated effort, grind a surface to an optical flatness, a process that is slow, communal, and deeply physical. This interdisciplinary dialogue transforms dry data into a vivid story. It replaces speculation with reproducible practice. It shows us that the ancient builders were not mystical figures, but peerless professionals whose work can be understood when we approach it with the same combined intellect they themselves must have possessed, blending observation, mathematics, and hands-on skill. The complete picture of ancient engineering is a mosaic, and each tile is placed by a different expert. The final, beautiful image reveals a simple, profound truth, that human achievement at its greatest has always lived at the crossroads, where the curiosity of the scholar meets the wisdom of the maker. This silent conversation between stone and sky forces us to rewrite a quiet assumption buried deep in our historical imagination. For centuries, the narrative of human progress has been a simple, upward line, a story of gradual improvement from crude beginnings to our current pinnacle of technology. In this story, the ancient world sits on the lower rungs, a primitive prelude to the real achievements of modernity. The flawless geometry of a pyramid corner, the seismic resilience of an Andean wall, the machined finish of a granite box, these are not mere footnotes in that story. They are profound anomalies that shatter the timeline. They force a humbling and thrilling reassessment. What does it mean to be advanced? Our modern definition is tied inextricably to electricity, to metallurgy, to digital code. But the builders of these sites present us with a different model of sophistication, one built not on complex machinery, but on an unparalleled depth of understanding. Their mastery was not of silicon and steel, but of stone and sand, of leverage and patience, of celestial patterns and material properties. To label their world primitive is to make a critical error, to judge them by the presence or absence of our tools, rather than by the breathtaking results of their own. A culture that could calculate true north by watching a star's path for a year, that could engineer a wall to dance safely through an earthquake, that could achieve optical flatness on granite with a wooden beam. This was not a society stumbling toward discovery. It was a civilization operating at the peak of its own scientific and technical paradigm. Their knowledge of materials science, of how different stones fracture and polish, was empirical, earned through generations of hands-on experimentation. Their command of geometry was not abstract theory, but a living, breathing tool used to impose order on a chaotic world. Their application of mechanics, using ropes, ramps, and levers, shows an intuitive grasp of physics that we have simply automated, not fundamentally improved upon. This evidence compels us to shift our perspective. These ancient cultures are not steps on a ladder leading to us. They are parallel peaks of human achievement. They solved the monumental problems of their time: how to build eternally, how to align with the cosmos, how to create community through shared, generational work with the elegant tools and profound environmental wisdom available to them. Their solutions were different from ours, but in their context they were no less brilliant, and in their endurance perhaps even more so. This realization does not diminish our modern world, but it dramatically enriches our view of the past. It asks us to listen more carefully to the quiet intelligence locked in these stones, and to recognize that human genius has always been present, wearing many different faces across the long span of our shared history. The final image that emerges from these stones is one of profound human synergy. Across continents and centuries, from the desert heat of Giza to the thin air of the Andes, we find not a single lost secret, but a shared constellation of genius. These builders were neither sorcerers nor the passive recipients of otherworldly gifts. They were the ultimate practical scientists, the consummate artists of the tangible world. Their precision was born from a deep, interwoven harmony, a symphony played with many instruments. It was the intimate knowledge of a stone's soul, married to the eternal truths of geometry. It was the clever amplification of force through simple machines, guided by the relentless grinding science of abrasives. And underpinning it all, the most vital component, the patient, skilled labor of human hands, a river of wisdom passed silently from master to apprentice across generations. Their true legacy, therefore, is more than the silent, imposing monuments they left behind. It is a quiet, persistent challenge to our modern sense of superiority. In an age where we equate advancement with digital complexity and disposable speed, their work asks a different question: what is true sophistication? It asks us to reconsider where genius truly resides. The next time your gaze falls upon a photograph of those impossibly fitted walls, or you stand humbled before one in person, see it for what it truly represents. It is a monument to the limitless potential of the human mind, the calibrated skill of the human hand, and the enduring power of the human spirit when all three are united by a common, monumental purpose that stretches beyond a single lifetime. If this journey into the mind of ancient engineers has sparked your curiosity, we would love to continue the conversation. Share in the comments below which ancient site or specific feat of construction baffles and inspires you the most. And if you want to keep unraveling history's greatest puzzles with us, be sure to subscribe.